In the last lesson, we learned that Gibbs free energy is a way of looking at the combined effects of changes in enthalpy and changes in entropy for a given reaction. If delta G was negative, it means these changes in this reaction would be spontaneous. If delta G was positive, it would not be spontaneous. In other words, if we take this equation right here, but because we can't measure these things directly, we measure their changes, delta G equals H minus the absolute temperature times delta S, the change in entropy. Now, an interesting question would be, since there are a lot of things or processes such as freezing or evaporation, but also chemical processes that might have the change in heat, whether it's exothermic or endothermic, working at odds with the change in entropy, whether it's becoming more disordered or less disordered. In that case, the question might be, well, at what temperature will a system that is naturally non-spontaneous become spontaneous? Or at what temperature will a system that is non-spontaneous become spontaneous? I think I said that right. So, for example, consider calcium carbonate. By now you should know that calcium carbonate is definitely a solid. It is insoluble. It is the formula for lots of different minerals when they have slightly different structures, and you can have completely different properties. For example, marble is calcium carbonate, a very, very hard building material. Limestone, which Missouri has much of under our earth and under the topsoil. And of course, it gets leached away by water, and we have our famous Merrimack caverns and so forth. But limestone is calcium carbonate. Chalk is calcium carbonate. Lots of examples of minerals that have this particular kind of formula. And as you might guess, calcium carbonate does not naturally decompose into calcium oxide and carbon dioxide like you see here. And that's a good thing. I mean, you would hate it if the entire state of Missouri suddenly subsided and went below sea level because all the calcium carbonate decomposed, and Missouri would be just one big lake. Also, if marble and all the things that we've made out of marble, including many of the buildings in Washington, D.C., if those decomposed easily at ordinary temperatures, where would the buildings be? And of course, one might make a comment, well, having less government wouldn't be all that bad after all. Depends where you are in the political spectrum. But the question then would be, well, is there a temperature where calcium carbonate would spontaneously decompose to form calcium oxide and CO2? And before we answer that question, for those of you very interested in biology and biochemistry, there's an awful lot of thermodynamics that goes on in biology. And there are many, many chemical reactions that are essential for living things that do not take place spontaneously. In other words, their delta G is positive. But if some of these chemical reactions are working in conjunction with other chemical reactions that happen to have a substantial negative delta G, they can become spontaneous. And you might recognize, for example, the importance of the bite-sized energy that cells need when glucose gets broken down, adenosine diphosphate turning into adenosine triphosphate, the energy-rich molecule. And then once the ATP loses its energy as a result of losing a phosphate and that bond getting broken, that phosphate needs to be reattached to the ADP to reestablish the ATP. And for example, this can happen in glycolysis. So, back to our question. At what temperature would a chemical reaction that normally is non-spontaneous, would it become spontaneous? And the way that you do this is you take the Gibbs free energy equation right there, and you set your delta G equal to 0. Because 0 would be the cutoff. Anything less than 0 is spontaneous. Anything greater than 0 is non-spontaneous. So if you set delta G equal to 0 and you solve the equation for T, you can find out the temperature at which a reaction that is not spontaneous would become spontaneous, or the temperature in which a reaction that is spontaneous would become non-spontaneous. Now, just a reminder, notice that delta H is almost always in terms of kilojoules, and your entropy is almost always in terms of joules. That is why you need a conversion factor. You're either going to multiply the heat by 1,000 to convert the kilojoules into joules, or on the other side, the right side, the entropy, you're going to divide the joules per Kelvin by 1,000 to get kilojoules per Kelvin. Don't forget that. That's a common mistake. Let's take a look at this example right here. If we have this interesting compound, nickel tetracarbonyl, tetra means 4, the carbonyl is the CO there. If it could decompose into nickel and 4 carbon monoxide molecules, you'll notice the stoichiometry is a 1:1:4 ratio. We can calculate the delta H and the S values. We can look them up on charts, which is done down here in the chart towards the bottom in the solution. And so if you were to take the 4 carbon monoxide heats right here, multiply that by 4, the heats of the products, and here's your other product, which of course is 0 because it's a pure metal. We talk about the formation of a compound from its elements, so the formation of an element from itself is 0 by comparison. And we were to take 4 times a negative 110.525 and subtract my heat of reaction, we're going to get this positive value right here for my delta H. By the same token, if we take 4 times my entropy value plus my entropy value for nickel, remember, only crystalline structures such as metals have an entropy of 0 at absolute 0. So it is positive even though it's elemental. You take the sum of those, 4 times the 197.67 plus the 29.87, subtract the 320.1, and you get a positive 500 here. Now you can see when you look at these two values, this reaction is, as far as the delta H is concerned, it's non-favorable for it to be spontaneous. As far as the delta S is concerned, it is favorable. So the entropy favors a spontaneous reaction, but your enthalpy does not favor a spontaneous reaction. Then, when we take these values and plug them into here to calculate delta G, and we set delta G equal to 0 because we're trying to find the cutoff point as far as the temperature is concerned, you can see that we can make a reaction that is spontaneous become non-spontaneous, or vice versa, depending on the problem, at a temperature of 379.4 Kelvin. Now, the last main idea in this chapter, and an example of a problem, is relating delta G to your equilibrium constant. Now, before I do that, let me review. you can find delta G at least 3 different ways. You can find delta G by just looking the value up in a chart. You can find delta G by taking the Gibbs free energy of the products minus the Gibbs free energy of the reactants from the charts to find the overall Gibbs free energy change. We didn't have any examples of that. Or you could find delta G by setting it equal to delta H minus T delta S. So on an AP test or on one of my tests, you would be given charts for finding your delta H's, your heats of formation from their elements. The charts would also have your entropies, and your chart could also have your Gibbs free energy values for all of these different compounds. All right, example 19.7. Here we have the formation of ammonia. And in this problem, we are interested in 1 mole of ammonia. So if we want just 1 mole of ammonia, a reaction per mole of ammonia, we need to reduce the other coefficients in the balanced equation to fractions. And in this particular situation, we're going to use this equation right here that relates delta G, Gibbs free energy, to your equilibrium constant. So if we have a way of finding or obtaining our value for delta G, look it up on a chart, do the delta G of the products minus the delta G of the reactants, or to use the Gibbs free energy equation, delta G equals delta H minus T delta S. However you find your delta G, however you found it, you plug it in here. Here's that value of R. And please remember, very seldom now do we actually use 0.0821 like in our gas laws. Anytime we are working with joules of energy, we have to use 8.3145 because it is in terms of joules per Kelvin mole. My temperature has got to be in Kelvin. And so we're going to solve this equation for the natural log of K using regular algebra. And then we have to do the inverse log in order to find our equilibrium constant. And again, if the equilibrium constant is greater than 1, we know that we are going to have a reaction that is probably going to go to the right. And the more it's greater than 1, the more to the right it's going to go. And if it's less than 1, but of course greater than 0, that means we have a reaction that favors the reactants instead of the products. Here's another example of that kind of problem. But you'll notice that in order to get my right value of K, and some of you missed this on the previous test, we had to reverse a chemical reaction, which means we have to take the reciprocal of our value of K in order to get the equilibrium constant. In other words, it stands to reason that if, in this equation right here, if silver chloride does not dissociate in water to silver ions and chloride ions much at all, and its equilibrium constant is logically very much less than 1, that is 1.8 times 10 to the minus 10th, that the reverse reaction ought to be very product favored. That when you have silver and chloride ions in solution, they most definitely will want to precipitate and form silver chloride, giving you a huge equilibrium constant of 5.6 billion. That's 10 to the 9th. And again, we can calculate our delta G in this reaction given the value of K. So, backing up just a little bit, in the top problem, you were given delta G and told to calculate K. In example 19.8, you were given K and asked to calculate delta G. And that finishes the chapter.